introducing Nico and Jim Downing from the University of Cambridge, chemists who work on semantic problems in chemistry, which is very interesting to me because I've worked on similar stuff in biology. It's a really huge problem. It's a potential solution to huge problems. It's academically very interesting, and it's obviously of interest to us at Google. So they're going to tell us about what's eating scientific data, 21st century approaches to discovering chemical data.
Thank you very much for the introduction, David, and also thank you very much to Ellen Coe for setting this up and inviting us here. Unfortunately, Ellen couldn't be with us today, but yes, we would like to try and give you an overview of some of our work that's going on in Cambridge. We are working in the general area of semantic technologies as applied to science, technology, and medicine. Our particular specialization is chemistry, and we care about chemistry because chemistry, of course, is the central physical science which sits at the interface of many high-value industries and high-impact other sciences such as bioscience, pharmaceutical research, and so on and so on and so on. And one thing that we're seeing more and more is that exciting scientific new progress, product development, is mainly happens at the interfaces of a number of different sciences, chemistry being in the middle, but a reinterpretation of that from an informatician's point of view simply is that product development in chemistry, new chemical discovery, very often are data integration and data mashup problems. And of course, the one thing that science and therefore also chemistry do, there are three areas of activity all the time. It's data production, it's data analysis, and it's data publication. That is just simply what science does. And in chemistry, the sort of typical scientific discovery cycle is a little bit like this. You start off with an idea which you develop, you get funded, you then develop an experimental plan, you carry out your experiments, you record the results of the experiments, you process the data that comes out of it, you publish the data, and then you read a little bit and you use your own data and other people's data to generate more ideas, and you go around the cycle again. Now, virtually all stages of that cycle involve data, of course, but virtually also all stages of that cycle are disjoint. It is very, very difficult to bridge data from one silo to another silo along that route. And the main reason that they're disjoint simply has to do with the way in which science and chemistry in particular at the moment produces data and publishes data and communicates data. So if we look at data production in the laboratory and in silico, we see the following things. In the laboratory, what we do is we carry out an experiment and we record the experiment and the data that we generate in the experiment in a notebook. That can be an electronic laboratory notebook, or it can be on paper. But in any case, what we're doing is we're producing, in essence, a compound document. We're producing a document that contains empirical observations and data all mixed into one. However, the way in which we treat that document is entirely determined by the semantics of the document as opposed to the semantics of the data that is also contained in the document. So the document, if you will, determines the semantics of how we handle data. It's the same for scientific publication. So here's a typical scientific paper. That scientific paper actually contains text. It contains an awful lot of data. That data is entirely visible to a human. We see that sort of thing, but of course, because the semantics that we're dealing with are the semantics of the document, what a computer sees in essence is this, and a machine will find it almost impossible a priori to discover data in this sort of mess, and let alone understand the data, understand in inverted commas, and act on it. So the way in which we publish and communicate and exchange data in science quite often leads to data interoperability death. Another facet of that data interoperability death and of that negligence in terms of dealing with scientific data is the use of PDF across scientific communications. So even if we produce a digital document in which we could, in essence, discover data, we then usually convert it to PDF for the purposes of communication and for the purposes of distribution. And what that in effect means is that we take potentially discoverable data in a document, we convert it to a set of graphical objects without any related semantics between them, and then we're expecting a computer to try and sort of rediscover that data again. And as one of my colleagues, Peter Murray-Rust, says, it's rather like taking a cow, converting it to a hamburger, and then trying to convert the hamburger back to a cow. And of course, most scientists are entirely unconscious of that process, but from a scientific point of view, from a scholarly communications point of view, PDF is not a good thing. It's just another manifestation of that carelessness with which we handle scientific data. The second phenomenon, and this applies to data in silico, if you will, is that we quite often produce data in a particular vernacular. So here is a representation of an enzyme, neuraminidase, associated with the influenza virus. That's a representation of data that humans understand, but of course the underlying data looks something like this. It is structured data, it is in some form of markup. However, it is markup which only one particular type of software can actually deal with, one particular type of software can understand, and it is markup which is not universally used by other software systems. So if you will, that markup is vernacular. We have structured vernacular, but these sorts of vernaculars too lead to, in essence, data interoperability death if we really do work on the assumption that we need to mash up that sort of data with data from other domain sources. The need for mashing up really becomes clearer and clearer as you look across the whole of the pharmaceutical, life science, home and personal care industry. Very few pharmaceutical companies maintain a whole discovery pipeline in-house these days. And by that I mean a discovery pipeline from fundamental research going right through to the clinic. Rather, what they've done is they've chopped up that discovery pipeline and they are starting to outsource activities across that pipeline into smaller companies that specialize in a number of these activities. What it means, though, is that those pharmaceutical companies need to have a means to actually export their data out of their own system into the companies they outsource to, and the companies that are being outsourced to need to get data back into their client systems. So data integration really is a pressing, and data interoperability really is a pressing thing, and it leads to phenomena such as the formation of the Pistoia Alliance, for example, which is a conglomerate of a number of very large players in the pharmaceutical arena that tries to standardize data formats across the industry. Now, you may argue about how successful that'll be, but in any case, it's going on, and the lesson from it is that data interoperability is not about serendipitous reuse of data, that it is essential for integrated data environments. And we've just taken a day out from a conference here in Silicon Valley, Semantic Technologies, and that conference certainly seemed to be suggesting that this integrated data environment is starting to happen on the web now. We're starting to see more and more mashups, more and very large-scale mashups across very large parts of the web. So we do require exchange formats, and we do require, or at least so we believe, computable ontologies. Now, you scratch your head for a while and you think, well, where have I seen a situation before where data is in lots of silos, where it doesn't have meaning, where it's hard to discover? And of course the answer is the World Wide Web. On the World Wide Web, what you have is a situation whereby basically anybody can say anything about any topic. And what that means is that data can be in different documents, in different locations, on different servers. But it's all data that may or may not pertain to one single resource. In this case, we're using a polymer as an example. And what we as scientists really would like to do is we would like to be able to pull that data together, not just from the World Wide Web, but we as scientists have got collections of documents in our computers, in the information systems that we use, and so on and so on and so on. And we would like to bring that data together to discover it and to mash it up and to reuse it. So if you think about that, the fact that the World Wide Web has the same sort of problems that we face in science of data interoperability, data discovery, unstructured data, you might ask yourself, well, has the World Wide Web also evolved solutions that might address some of those problems? And the answer is, again, so we believe at least yes. Data discovery and data structuring in the web is facilitated by extensible markup language. Data integration is facilitated by a technology called the resource description framework, and I'm going to explain that in a minute. And meaning and true data interoperability can be facilitated by the use of ontologies if you decide to go down that route. So let's examine some of these technologies in slightly more detail. In Cambridge, and actually even before our time in Cambridge, we've been busy developing chemical markup language. Chemical markup language was developed and is still being developed by Peter Murray Rust and Henry Sepper, and it caters for a wide range of chemical data. It describes molecular structure, but also physicochemical properties, spectral information, crystallography, computational information, and so on and so on. The whole gamut of data that you encounter in chemistry. Here's a very simple example of what CML could look like. It's a description of a molecule there on the left, and you see that the whole document talks about a molecule, so we've got the molecule element as a container. The document contains atom arrays and bond arrays, which in turn contain atoms and bonds. They're literally just lists of atoms and bonds occurring in the molecule. And the first atom is an atom of element type carbon. It has an ID and an X and a Y coordinate, and this sort of representation in essence allows you to construct that sort of representation there on the left. And that atom there is connected by the first bond here to the next atom along the list, A7 and A9. The bond in itself has an ID, and it's a bond order 2, so it's a double bond somewhere there in that molecule. You can extend these sorts of rigorous and complete descriptions of small molecules to fuzzier materials such as polymers and nanostructured objects, and that's something we've been working on recently in Cambridge. I'm not going to go into how this document works, but we can actually introduce fuzziness and stochastic computability into XML, and we can treat attributes in an XML document as computable free variables if we want to, which is kind of a new concept on the side for yeah.
What about MMSIP? You're familiar with that? So that's sort of the replacement for the PDB file format for protein crystal structures, and it embeds a lot of chemical information for polymers, for example. Are you familiar with it?
I'm not familiar with it, but when you say chemical information for polymers, then we're now running into an ontology problem, because when the protein chemists say polymer, they mean something completely different that I mean when in biochemistry and protein chemistry, a polymer is just a single macromolecule with a large degree of polymerization of amino acids. In materials science, which is my original provenance, a polymer is an ensemble of molecules, all of which have got slightly different lengths, slightly different architectures, slightly different properties.
So MMSIP might not have the expressibility to...
Exactly, and none of the representations we've had up until now can carry with that stochastic, or cater for that stochastic nature of polymers.
Like a distribution when you make a peg and you end up...
Yes, exactly.
Okay, so you want to describe the peg distribution.
Exactly. And we haven't been able to describe that sort of stuff, let alone search for it, or search over it as well. And this is exactly what polymer markup language gives you. So this is just a very short run through of the sort of XML tool stack for chemistry. There are many other markup languages which are pertinent. There's the analytical markup language, mathematical markup language, thermochemical markup language. All these sort of things interoperate quite nicely with CML and help you to deal with scientific data or with chemical data and to structure chemical data. Now, data interoperability is something that RDF caters for. RDF stands for Resource Description Framework, and the name is programmatic in the sense that it is a descriptive framework for describing resources. A resource in internet speak is everything that can be named or addressed, that can be real physical objects or metaphysical ideas even. And of course, RDF makes statements in a very simple triple form, almost human language, subject, predicate, object forms. And the reason for that is, of course, that a triple is the smallest irreducible representation of data that there is. An Excel spreadsheet, in essence, is a collection of triples. So column heading, polystyrene, row heading has glass transition temperature, value in the cell 90 degrees. That's, in essence, a triple. Now, what makes RDF special is not those triple statements, but rather the fact that every part of the triple has a URI associated with it. And what that, of course, means is that you can take statements from different domains and bring them together and mash them up in these sorts of triples. So you can construct these graph representations of your knowledge across different domains and across different namespaces. The namespace in the URI codes in essence for the domain. The analogy talking about Excel spreadsheets to this is taking every cell in your Excel spreadsheet, putting it into a different document somewhere on the server, but because it has its whole address space with it, by deploying one query, you could, in essence, bring the spreadsheet back together if it was expressed in RDF. So here's a way to...
It also gives the advantage that you can now normalize your spreadsheet and just references to canonical instances.
That's right. That's absolutely right. Yeah. So here's a way in which chemical data, it's actually very trivial, can be expressed in RDF. The serialization is N3 here, so we've removed the URLs for better readability. But you see the triples. We're talking about benzene again. Benzene is a molecule which has a property here, which is a boiling point, and that boiling point has a value of 80.1 and it has a unit of degree centigrade. And by the way, that boiling point also has a measurement condition, which is a measurement pressure, which in turn has a value of 100 and a unit of kilopascal. So that's a way of actually describing minimum information requirements as well. And you can see how we chain triples together and how we chain information about objects together. So the benzene, or the molecule benzene, is connected to a property, which in turn is connected to a measurement condition, which is specified as a measurement pressure, and so on, and so on, and so on. Now, there's a lot of chemical data now in RDF coming on stream in the form of DBpedia. For example, there's rdf.openmolecules.net, and there's also Freebase, which contains a significant amount of chemical data right now. So,
you know MetaWeb is just up in San Francisco.
Right. There is one small point, though. For true data interoperability, the ability to just mash up by matching graphs really isn't enough. I've got concepts in my document here, such as a boiling point and a measurement pressure and the notion of a molecule. And really, if you want a machine to discover data associated, well, a machine to understand data associated with those concepts, and to understand whether it can, if it finds those the same concept in two different documents with data associated with them, whether it really can bring those two together, it needs to understand, well, are those concepts the same? Do I mean the same thing when I talk about a polymer, and do you mean the same thing when you talk about a polymer? So what are the axiomatizations? And of course, for that, you might want to consider the use of ontologies to clarify that relationship. And in Cambridge, what we've done is we've developed a set of ontologies called, collectively known as ChemAxiom. They are a number of interoperable ontology modules. ChemAxiom ChemDomain, which is one module in this, clarifies a number of fundamental relationships in the chemistry domain. So, for example, it deals with the relationships between molecules and substances. That is of importance when we're talking about the sorts of things that we've just been talking about, polymers versus macromolecules, and what my understanding of those things is. It deals with identifiers. What are identifiers for a molecule? How do they relate to a substance? It deals with roles. So what do I mean by acid? Do I mean a molecule that acts as an acid, or do I mean acid, the substance in a bottle that sits on my bench, and that is sulfuric acid? Those sorts of things. ChemAxiom Poly, then, is an ontology that allows you to talk about the properties of these molecules and substances that ChemAxiom ChemDomain defines, and ChemAxiom Metrology is an ontology that allows you to speak about how these properties were measured. And then, of course, we've also got ontologies, because we are polymer chemists originally, that deal with concepts in the polymer domain. There's also an ontology at the moment for chemical metadata, which is under development. Now, here's a summary of those ontologies. They were developed with the use case of describing chemical data in mind. There are other ontologies in the chemical domain which do different things. So there are ontologies of chemical reactions, there are ontologies of chemical compounds and their biological functions, and so on. And ChemAxiom interoperates quite nicely with all of these ontologies. So between them, they actually cover a wide area of chemistry. The platform has garnered some significant interest internationally. We're working with the University of Ottawa, the Royal Society of Chemistry, and the European Bioinformatics Institute to actually, between us, come up with a solid platform and maintainable platform for the further development and maintenance of these ontologies. And we're at the moment expanding ChemAxiom to also deal with data from computational chemistry codes and crystallography. Now, how do these ontologies work? Well, here's an example of the formal computable definition of a chemical substance. And basically what this document does is it defines a chemical substance as the union class. So we're doing set theory here, and we're modeling the world in terms of classes. And a chemical substance in this document is defined as the union class of the class of everything that is composed of molecules. So substances, bulk substances in the bottle, are composed of molecules. Right? and the class of everything that is composed of other substances, and that gives you recursion and therefore allows you to model mixtures and formulations and all that sort of thing, and the class of everything that are chemical elements. So the union class of all of that is defined here as a chemical substance. Now we will always argue about these definitions and the axioms, but at least I now have a computational way of actually checking what it is that I mean by substance and therefore what the data that I've associated with that concept means. And interoperability now comes from this combination of data in RDF and ontology. So here is more data about benzene in RDF. It's the same thing. We're saying that benzene, only this time we're talking about benzene, not the molecule, but benzene, the substance. We're saying that benzene, the substance, has a property which is a density and a boiling point, and the boiling point has a value, and it was measured by a measurement method called ebulliometry. And here, by the way, you see the mixing of various namespaces and various URIs and actions, because you see the Q names are drawn from different domains. So that's the RDF. Now then, I can look up what some of those terms in my RDF mean. So I said that the boiling point was measured by ebulliometry. Well, here is the definition of ebulliometry in chemaxion metrology. It uses an instrument called an ebulliometer. It is a thermochemical analysis technique, and one axiom that isn't shown is that it returns values of dimension temperature. So if now someone in their documents or in their data collection had a boiling point that was measured by ebulliometry, but where the unit of the value of the boiling point that they gave was centimeters, then I could immediately use this ontology to check, well, actually, is their understanding and my understanding of the boiling point the same, and therefore, can I bring the data here, or do I need to be careful?
Be a mapper in here
that's right.
Between temperature and height, or
right.
pressure and
right.
Okay.
Right. Now, we've talked an awful lot about markup, and that markup is all nice and well, but the question that you should be asking immediately is, dude, how do I get that markup into my documents and into my information sources? Nobody wants to have to author that sort of stuff by hand. How do I do it? And there are two answers to the question. The first one is you introduce markup a posteriori. So you have a document, you've written it in the normal way, and you then try and retrospectively mark that document up. There's an awful lot of legacy data that we have where that is the only way of getting markup into documents. To do that, we have developed a software robot called Oscar, which we call the journal-eating robot. And literally what Oscar does, it takes journals, documents, other scientific publications, and it tries to read it to parse the text, and using a natural language processing workflow to extract entities, actions, and so on from the text. So here's an example of the type. Here's the beginning of a chemical paper. Here's an example of the type of markup that Oscar returns. It discovers chemical compounds, it discovers certain ontology terms, it can discover reactions, and so on.
I can definitely see identifying terminology by standard vocabulary,
yeah.
But those sentences can, especially in scientific papers, be extremely dense
yes.
and often ambiguous.
Yes.
And so how are you ensuring that the NLP system is actually coming up with the right ontological representation of a statement?
Right.
Is it manual verification and acceptance of a certain error rate?
Right. The question was that chemical papers quite often are very dense, and that there's ambiguous meaning in a lot of those sentences. And how do we ensure that our natural language processing can come up with the right sort of ontological association with the entity that it may have discovered? The answer to that mainly is that disambiguation is something that we don't touch where we possibly can. So we deal with entities, with pure chemical entities at the moment, and a pure chemical entity is relatively easy to identify and unambiguous. Oleic acid is always going to be oleic acid. In terms of actions, how these entities are connected to other entities, that's a more difficult problem. And that's something that we're working on, but we haven't touched it. We haven't touched it so far. So right now we're just literally trying to get data out, and we're trying to get entities out, and their disambiguation problems are relatively sparse.
If someone else were to develop a similar ontology for a different domain in science, would your program more or less work out of the box, apply to say biological papers, or
for the entities, the named entities, it could be retrained? Yes.
Yeah.
I mean, obviously for this kind of deeper NLP stuff, you need to go through and build the different patterns.
So Oscar is relatively, well, Oscar can be relatively domain agnostic in the sense that it relies on a number of external resources such as external ontologies. Jim has pointed out that we can retrain Oscar. Also, the natural language processing that's actually going on in Oscar is not particularly deep. So we have discovery of entities in terms of either lexical matching or in terms of probabilities, right? We can work out probabilities of whether something is a chemical entity or not, and that's about as far as it goes. We do this using n-grams and that sort of thing. And it,
We're at 30 minutes in.
so yeah, sure, and I'm almost done. So the way this works out then is, here's an example of Oscar markup. And I've taken the first sentence of that paper that I've just shown you. And the first sentence reads, oleic acid-coated magnetite has been encapsulated in biocompatible magnetic nanoparticles by simple emulsion evaporation method. Once Oscar's finished parsing that sentence starts to look a little bit like this. And as you start reading here, oleic acid we've discovered as a chemical entity, and we have discovered it on the basis of simple lexical lookups. So one of the resources that Oscar uses is actually a lexicon of a very large lexicon of chemical terms, Kebi in this case, and we associate the information that we have discovered it through lookup. Kebi, together with the markup. We've also associated structure markup with the term oleic acid, which we get from our chemical ontology here. So we've got a small string and we've got an inchy string here. However, there is another entity in that sentence called magnetite. Now, magnetite we didn't have in our dictionary, and magnetite has actually been discovered as a chemical entity using an n-gram score with a given probability, and we associate that information, both the probability as well as the provenance of that markup, together with the concept.
So you're embedding details of how you figured out what
that's right.
was
Yes.
in the markup.
Yes, that's right. Because I mean that's one way of ensuring.
So later, if someone is actually processing this,
yeah.
they can have priors that
yeah.
I don't believe n-grams. So
that's right.
They'll just throw away all those.
That's right.
I believe the
yeah.
string matching.
That's right.
Okay.
Yes, that's right. Also, this is annotation inline. Oscar also produces standard annotation. So if you didn't want to have multiple annotations, or you chopped up your entities at different, you changed your tokenization. In essence, you could deal with that. We can not only do that for chemical entities, we're also starting to be able to do it for procedures. For example, here is a synthesis procedure that contains a number of different entities, such as reagents, chemicals, that also contains solvents, that contains quantities, and that contains actions. We can discover and mark up all these sorts of different types of objects, and we can hold them in CML. And once we've done that, and we actually throw the natural language away, you can still understand what's going on in the document. We're taking a reactant in a certain amount, dissolving it in a solvent of a certain amount, adding more reactants with stirring, filtering, evaporating, adding solvent, filtering, and drying it. And of course, once you have that information in that form and marked up in XML, you can then pass that on to synthesis robots and to other information systems, and you can do searching and discovery and so on. Now, I wanted to give you a quick demo of what Oscar actually looks like, if our AV system doesn't scupper us right now. Here we go. So here is a typical scientific paper, as you would read it in any journal. The only thing, and as it gets published on the web by STM publishers, the only thing that we've done is we've taken all of the graphical guff out that the publishers usually put in, and we can now actually, you see, it contains a number of chemical entities. It contains data. It contains all the usual things that you'd expect in a scientific paper: introductions, experimentals, and so on. And we can now actually ask Oscar to parse this thing, and it'll go away and think about it. And after a while, it will have come back with the markup. It will have discovered chemical entities. You see, it's discovered a heck of a lot of polymers here. It's discovered not just the names, but also abbreviations. And it will sometimes we'll be able to associate a structure with the discovered chemical entities. So here we've got water, for example. We do get a structural representation of the thing. We have got more complex molecules where we can do that as well. N-vinyl formamide. No, that doesn't seem to work. But here's vinyl acetate, for example. And here you see again the sort of markup that we've associated with it in the text. If I click on it, I can get to more information about the molecule, such as synonyms, smiles, inchi keys, and I can hook through to other information sources where I could find out more about the
Now,
the thing.
I see there's an option there to add vinyl acetate as a stop word.
Yeah.
Is that a global effect that will then have an effect when you parse future documents?
Yes.
Or
So,
is that
yes.
intended for the document you just worked on?
No, it interacts with the resources that Oscar uses, and it adds it to a list of.
So you effectively have an ongoing vocabulary.
We have an ongoing vocabulary. That's right. Yeah. Okay. So this is Oscar, and of course now this is introduction. This is introduction a posteriori, but it would of course be much better because this sort of information archaeology is lossy to do it a priori. And if we do it a priori, we've developed authoring tools that plug right into the authoring environment that most scientists use, or chemists use at least, which happens to be Word, and which will watch you as you introduce chemistry into the document and introduce markup. So here's the plug-up in action. We can introduce chemistry into Word documents, for example, by importing a CML file into the document, or by actually selecting molecules from a gallery of molecules. It turns out many chemists in their day-to-day lives only work on a small subset of molecules, and so we can deposit them in a gallery, and then as they write about them, they can choose it and introduce it into their Word document. Or another alternative is that Word will actually watch you type, and as it discovers potential chemical entities, it will mark these things up using the SmartTag technology. You can then confirm that indeed, yes, this is a chemical entity by converting it to something we call a chem zone. And ultimately what this has done is that it has deposited a CML document into the Word OXML document. We can, now we've got two chemicals in a molecule, we can look at those things in a molecule browser, which is part of the document. It's not so useful if you've got only 2 molecules, but the typical chemical paper contains 20 to several hundred molecules. That sort of thing becomes really valuable. The representation, as you will see in a minute, is actually the graphical representation in the document is decoupled from the underlying data, so we can change the representation. We've just changed benzene to phenyl hydride and now to C6H6, but it all points back to the same CML document. Here's an.
Earlier, I noticed you were using Q names that pointed to Wikipedia.
Right.
But I see that URI, as really a reference to a document about benzene and not really the authoritative statement. This is the molecule benzene, or this is the solution of benzene.
That's
right. Do you guys really use that, or do you have some sort of...
No, that was just an example for argument's sake. So while the demonstration was running, what it also showed was we introduced a second benzene molecule, which was independent of the first one. We could change the representation of that one independent of the first one. So this is copy by value, but we can also deal with copy by reference. So we can couple several representations to one underlying document. That's Chem for Word. There's more information on Chem for Word at that website. We'll be releasing it very soon, hopefully as open source code on Codeplex. So
it's basically just a plugin.
It is a plugin. It is indeed a plugin for Word, yeah. So the next question you should be asking myself, well, dude, where are all my data sources? Now I can do all the markup, I can introduce the data, where do I get my chemical data from? And that is a very, very good question. Chemical data is very different from other types of scientific data in the sense that very large businesses have been built atop of chemical data, and business interests are very entrenched, and it is actually very hard to get hold of open chemistry data. It is stifling the progress of science at the moment. We are hoping that the increasing drive towards data integration, the need for data integration, together with the increasing availability of the semantic technology stack and other technologies that we've just been demonstrating, will ultimately drive the uptake of those technologies. Yeah. And it is indeed a universal problem, but it is a problem that together I think we as scientists and information, or the more forward-thinking information providers, are cracking, slowly or surely cracking. So the next thing is, but dude, how do I publish semantic linked data on the web? And with that question, I would really like to hand over to Jim Downing, who has developed a fantastic system for data publication on the web, and he's going to conclude the talk by telling us about that. Thanks, Jim.
Thanks, Nico. So as Nico said, I'm going to I'm going to kind of give you a quick introduction to a tool we're developing called Lensfield. And what Lensfield is it's a system for the generation, management and publication of semantically rich linked data. Kind of at a top level, it fits together like this. We take a software build metaphor approach to the data processing. We produce a simple linked data web application and provide automatic methods for deploying the data with this application that provides Sparkle endpoints and other bits to make the data more machine discoverable.
Did you say Sparkle?
Yeah, okay. Yeah. And we kind of help with the management of the whole process and of the data by automating and helping with backup procedures and version control. But just to step back for a moment, Nico alluded to it earlier, but why do we want to do this in the first place? And why do we actually care about linked data? Well, this is kind of my simple model of science from 30,000 feet. It's about observing the world, forming hypotheses, forming a model, using your model to make predictions, comparing the predictions against experiments, and refining your model. Now, at its best, science is a virtuous cycle where people can build on each other's results, they can share and collaborate on their hypotheses and build their models together. But at the moment, this really isn't happening, and we think that linked data could really reduce the kind of friction in the cycle and a lot of the disconnects. When people produce research, they don't produce data, so people can't observe that data to build further hypotheses. Now, linked data can help, sure, with the data size of things, but it can't really help so much with sharing and collaborating on models. But that's starting to happen as well. For example, there's a site called myexperiment.org, which was developed and is run by the universities of Manchester and Southampton. And that basically provides scientific...
Carol Goebel?
That's Carol Goebels, yeah.
Okay, yes. So I've known her from years ago.
Right.
That's great.
What it basically does is it allows scientists, specifically data processing in informatics, to share their informatics workflows. So here we can see that you can share your workflow. Other people can download it and run it, validate it against their data. You can tag it and follow people and all that kind of jazz. And importantly, going back to Nico's availability problem here, we can have clear statements of open licenses. So it's clear we wanted to get linked data. We wanted to see how far we could push it, but we were really having problems with deploying these tools and introducing these technologies in our department. Even the PhDs and postdocs, who are all very, very smart, had problems with semantic technologies. They're new to them, and when you're introducing something new, you really want kind of that Python factor of simple things being simple and complex things being possible. Kind of, you put in a little bit of effort, you get an awful lot of bang for your buck in the first few days. And semantic technologies really aren't like that. It's really sticky. Part of that is because of the huge variety of technologies you need to know. This is a really, really big technology stack. Somebody who comes out of a PhD in the lab is not going to know about how to get a web app working on a server, let alone about what HTTP is, let alone about content negotiation, Sparkle, RDF. But there's a much more fundamental problem that actually causes the really long delays, which is just remodeling the world as graphs when you've been used to tabulated data and relational databases and this kind of stuff. But the reason you actually bother with these kind of complex technologies is that you've got faith that in the long run you're going to get an awful lot back. You're going to get a lot more capability. You're not going to stick yourself to some simple abstraction that's going to kind of peter out once you get down the line a bit, or isn't going to get a network effect and that kind of thing. So we really wanted to come up with some kind of hybrid that let people have simple tools and abstractions while they were learning, but once they got to be experts and started to dig into these things, just got out the way. We didn't want to put a limiting abstraction onto them so that it was, we made it simple for them, but it would limit them later on. So we're really trying to come up with that abstraction. So the first thing we went for is we built a client-server app that kind of dealt with all the semantic bits and dealt with the Sparkle. And that was all kind of going okay. But what we realized actually is that the data publication is such a small part of the scientist's working practice, that it really wasn't compelling for them. We realized that if we wanted to kind of hit the sweet spot for getting these semantic technologies into their thinking and into their workflows, we really had to reach into their data management, reach into their data processing. So the kind of the environment we were starting to work in that case is that, as Nico pointed out, there's a paucity of good quality public data in chemistry. PubChem and ChemSpider are both starting to go places with that, but it's still early days, and we're hoping that through these tools we'll aid the cause. It's also the fact that data management is a really rare skill. People don't come out of PhDs knowing about what to do with their data. Really, they probably know that it's important to back up, and they'll know how to burn a DVD. But certainly the kind of information management you need to be a good data producer isn't there. Automation software like the workflows engines that was behind that myexperiment.org, that's called Taverna, they're starting to get adopted in places, but they're not the right solution for everything. And it's still early days in the software. That's an artifact of this disconnect that's happened in e-science/cyber infrastructure, that we've had, by and large, we've had computational people developing infrastructure, and we've had scientists doing science, and it's been hard to get the scientists to use the infrastructure, or the infrastructure people to actually go and make it useful for scientists. It's starting to happen, but again, it's not there yet. So for all of these reasons, we needed a plan B. We needed to really help them get from their raw data, help them to do it right, help them to get the quality in there, and then we could think about publishing the linked data at the end. We needed one of these, so we started to develop it, and it was Lensfield. So next few slides are kind of Lensfield's design aims, what I tried to achieve with it, and what we're trying to achieve as we go forward with Lensfield. We want to kind of promote best practice. We want to give you default ways of doing the right thing and making it really easy. So from that point of view, we version control your data alongside the scripts that you write and the code you write to process the data, so that you can go back at the end of your PhD, if you need to rerun any results, you can go back and you can work out why your script produced the results that way. If you'd failed to version control either, stitching it back together would be a nightmare. At the same time, so we build the whole thing on top of Mercurial, which gives us a nice version control system and ways of sharing data. It's a distributed version control, yeah.
Okay. Was that an important attribute?
It might well prove to be. I think the main thing that the distributed version control gives us is it gives us flexibility in the architectures we build. You can have centralized systems using DCVS, but you don't need to. So we've got at the moment we have a really simple abstraction that just allows you a snapshot, which takes you through an interactive query of making sure everything's either under version control or ignored, and it's all clean. And then we have backup, which does a push to a central server. So we can have. So,
for example, if you have a directory and some core raw data that you want stored in a version control, but then maybe there's something you run a simulation that takes 2 days, generates 100 gigabytes of data, you don't want to put that in your version control, but you have all of the instructions to recreate that data. You would go through in this step and say, do not snapshot or do not back up this 100 gig part of it because it can be reproduced.
Exactly. On the other hand, if it was an indeterminate process, you'd need to know what that run was, and you might want to keep it. Yeah, absolutely. You've got the flexibility there. And the backup, which pushes all of your changes to a backup server. And that's the other thing that Mercurial can give us. We don't have to have one central server. You can push backups to one server. You can share the data by pushing it to another one. On the data processing side, I've mentioned this build abstraction. I really wanted to focus on describing what the process was, rather than scripting what was meant to be happening. Especially because we're not going to be able to wrap everything from the start with this system. Half of these programs are running on a Fortran that only runs on the VAX down the hall. Half of them are running with little scripts in whatever language the scientists learned when they were doing their PhD, and so on and so on. So it was really important that whilst we do want to automate as much as we can, Initially, we just had to be able to describe it. That's the minimum. When it comes to the linked data, we were just aware that it had to go out. It had to be kind of invisible on day one. We had to do it automatically as far as possible. We've put a lot of effort into writing converters from those vernacular formats into CML, and from there into RDF against the OWL ontologies that we've got. Through that, we're promoting the adoption of these standard ontologies, so there will be a corpus of data out there. Basically, it's minimizing the cost of the scientists of producing this stuff. We had a big non-functional requirement, though, as well, which is that we're trying to get a new tool, and we're trying to get people to adopt it. And scientists are fairly resistant to any kind of new productivity tool if it doesn't give them productivity. And the whole point of this is it has to reward the first user on the first day they use it. There was no way we could say, use this for a month, and then you'll find the benefit in having version controlled your data. There was no way we could say, well, use this because when 100 of you are using it, you'll find you can all share your data and it will be cool. And the real thing that we found that people went for in this kind of 0-point benefit is the idea of having your data and process backed up is very attractive. And the other thing that we'll come on to is that we can do some fairly fast visualization that they're not able to do. Well, they don't regularly do at the moment. We can make that very easy for them. The other part of it was that to try and reduce the barriers to adoption with the tool, it meant that we couldn't really get the users to come to the tool. We needed to take the tool to the users, and that meant running on the workstations. There's an awful lot of data processing happens on the workstation still, or even if it's happening in the cloud or in a distributed cluster, it's being launched from the workstations, and that's where the data management happens. So yes, we've made it as a workstation running app. Just to come on to the compulsory bit of layer cake, as I've mentioned, there's some version control which is happening in Mercurial, and there's a whole load of Java libraries. We have our linked data, our RDF infrastructure is all in a package called Sesame. That provides our kind of primary abstraction and the triple store and all this kind of stuff. And we have a wealth of functionality in existing Java libraries. The chemical information community have been primarily in Java through the chemical development toolkit, CDK, and with Jumbo and with a lot of other developments. So we couldn't abandon that legacy. The rest of Lensfield is built in a language called Clojure, which is a Lisp that runs on the JVM. It's a functional Lisp. My first reason for choosing it was that it was functional. I had this brief dalliance with Erlang last year, but for the lack of Java interoperability, it was clear that wasn't going anywhere, although the distributed computing model in Erlang was absolutely fantastic.
Specifically, what is an advantage of having a functional programming language?
So
does it map better to the domain?
My belief about the functional programming languages is that as multi-core, as basically as computers scale with cores now instead of as processor speed, it's going to be important if you want to make this stuff accessible to programmers who aren't like the top 2%, that you've got to have an abstraction that stops them hanging themselves. It's why memory management is why Java and .NET took off, and I think functional languages are going to be what helps multi-core take off. So it isn't really that I've got a big thing about functional languages. I didn't do a CS degree and do...
Well.
Right.
It doesn't run under Java. So.
No. Okay. Haskell's also strongly typed, which is, so last year. Clojure's also dynamic, so it helps us stay cool. And another feature of Clojure being a Lisp is something that I'm not going to claim any great expertise in, but it has had some interesting properties that we're hoping to, in the coders data kind of environment, that we've taken some advantage of in the build structure. So diagrammatically, the way you describe one of these data processes, this describes a build we constructed for a chemical engineering collaboration we had in the university. They'd done some Gaussian calculations, structure determination and thermochemistry calculations. They'd got a lot of output files from that process. They came along with 200 output files, and we stuck this together in a few minutes and did the data processing, and were able to kind of jump through their data really fast. What we want is, what we want is to visualize this stuff in a web application, this linked data application. To do that, we need some RDF, and we probably need some pretty pictures. To get the pretty pictures, we need the CML. To get the RDF, we need the CML as well. And to get the CML, we use a converter. And these were all converters we had in place already, which was fortunate, but it wouldn't be hard to kind of do these kind of migrations. Incidentally, so the way you express the build is in terms of these pink arrows. You're a function of your precursor and the function that produces you. The data conversion isn't the order of it you don't care about as a user. The system works out the order and kind of evaluates it for you. What it looks like in Lensfield, it looks like this. I'm not going to go into the syntax. It doesn't really matter except to point out there isn't an awful lot of it. That's the main thing. This isn't a file that gets passed and read in and then runs a system. This is the program. And that's been the neat thing about having this macro-based language around. We didn't have to write a separate component to read this stuff in.
The only thing I'll say is that it looks a lot like makefiles.
Yeah. Yeah, so I was strongly inspired by making this. So the way these things get expanded is that source macro expands out to a set of files. It's on the left-hand side with the Gaussian files. The CML product gets expanded out to a set of output files from the input files, and a conversion. As the conversions run, they can start to put their processing information into this build structure. So the build structure is that data structure is getting expanded and enriched as you go along. Files might get dropped out if it's a repeat run, like make. You don't have to redo files that are already built. And the point of keeping that log information is that by the end of the run, when everything's been evaluated, we've got all of the provenance of the run as it happened, as well as the data that we've got from the files. So we've got this, and using the URIs, it's all mashable up. So we've got a complete build structure. We've got a complete record of the process, and we can convert that to RDF, and we can drop it out into the triple store as well. I'm going to skip very quickly through the.
I just wanted to ask really quickly to go back to your rule page one more. Yeah. So my interest is how to build workflows automatically.
Yep.
By eluding certain aspects of the workflow, specific aspects, and generalizing them. So you know, for example, to go from an HTML page to a PDF page, that's a generic rule that just calls XPDF or whatever application.
Yep.
And then when you describe your workflow, you say, I have an HTML and I need a PDF. It's going to automatically infer that build.
Yeah.
Into your system?
We have an autoconf that can generate this. We can have a registry of converters, and you can build up all of the paths, and you can do path optimization and all this kind of stuff. For standard flows, that's great. If somebody had needed to do some heuristic calculation on the CML, then all of a sudden the autoconf isn't so valuable. So it's something we've done because it was interesting. So I've shown kind of just straightforward data conversion, straightforward make. We can do other things as well. We have a system called Crystalli, which I possibly don't have time to show. Or should I show it anyway?
Go right ahead if you have, if there's no one here afterwards, it's fine. And if not, we can just look at it on the laptop.
Okay. So what Crystalli does is it crawls the scholarly publication literature, and it looks for crystallography information, follows links, tries to work out the link text, follows it to the crystallography files. So, for example, here we've got Acta Crystallographica E, which is a fairly unique type of publication. It only deals in publishing crystallography reports. But it shows that we can drill down, and we can have a look at the structures that were published in the article in that issue of the publication. Oh, we've compressed a little bit there. We can go and see a larger report of it. And if it loads...
You might be having that weird problem where if you have dual display, it probably shows on your monitor.
Oh, there we go. So there we go, and we've got these neat visualizations allowed to spin the molecules around when the laptop's working. This is the work of Nick Day, who's also working on this Lensfield system now. And this was just to say that we'll be moving that publication crawling and grabbing this supporting information. We'll be moving this under Lensfield in the next few months.
Now, do you effectively give it a journal as a seed, or can you give it an article and then we'll go explore all the references in that article? And
I believe it has the journal's the seed, yeah. and it works through the articles. I mean, this is admittedly a really brittle system. It's also one of these things where we're adding some frosting on the top. We really hope the publishers are going to start doing this soon. We'd really like to start having data feeds in Atom. We'd like to start them to start publishing in ORE as a way of describing a boundary around some resources on the kind of the global graph in RDF.
Are any of these new open journals doing it right? Like PLOS?
I haven't seen what PLOS do. Most probably not. Most probably the semantic publication of saying, here's the supporting information, isn't. And the reason for that is that you don't want to irritate your authors. That's one of the big things about being a publisher. The people who are doing the best, and we've built this system to harvest Nature Chemistry, which is a new title. They're very good at publishing their data. They go to a lot of efforts to get it into the right formats. They publish CML right off the web page. They're not quite fully semantic yet. They've got bits of RDFA for the bibliographics.
Yeah.
But that takes such an amount of manual effort for them to do that because they can't demand that their authors do it all the time. So they're the best, but it really does require getting data publication into the authoring workflow, because really the authors probably lost those molecular representations. NMR spectra regularly aren't recorded in open standards and submitted with the journal article. They'll print them out, paste them into their book, and so on and so on. And we can also use it for automating our natural language pipelines as well. This is the Oscar Opsin tool that Nico showed earlier. We can use it to, for example, we can use Lensfield, for example, to download PubChem abstracts, grab out the structure annotations and reaction annotations, convert them into the standard formats into RDF, and then visualize them as well. So this is just an example of the visualizations that people found really useful. It's very simple, but the ability to be able to throw in your data as soon as it comes out, to see a list of all your data, and then to be able to come up and have a quick look at the 3D representation and at all of the parameters is really a strong win on the kind of day one win. So just as a summary, what I think we've managed to achieve already with Lensfield is that we've got this idea that we've got this day one win for the scientists, mainly through backup and visualization. It was a matter of seeing what caught with people. And the long-term benefits through having that provenance information and the version control and the linked data publication, they're going to be the longer-term wins. So what I hope we've managed to show you in our hour is that there are chemical markup languages like CML and PML available. We've got a whole RDF tool stack for turning these into semantic data, turning them into linked data on the web. That ontologies are really a new and nascent thing, but there's some traction there, and this is going places. And that we're moving into the publication as well with tools like Lensfield. We're supporting that a lot better. But the reason we're doing all of this is that data availability is still a problem in chemistry. And that's the one we hope to crack. These are the folks that worked on the tools we've been showing today and on the ontologies. And these are some of our collaborators as well, so many thanks to all of those. Thank you very much.